What are wormholes? A deep dive into the mysteries of space-time. Introduction. The universe is vast, enigmatic, and often defies our intuitive understanding of reality. Among the most fascinating and mysterious concepts in modern physics is the idea of a wormhole, a theoretical passage through space-time that could connect distant parts of the universe or even different universes altogether. Wormholes have captivated scientists, science fiction writers, and the public alike for decades, offering tantalizing possibilities such as instant travel across cosmic distances and even time travel. But what exactly is a wormhole? How do they fit into our current understanding of physics? Are they real or just mathematical curiosities? This article explores these questions in depth, outlining the science behind wormholes, their theoretical types, their potential implications, and the challenges that face these extraordinary phenomena. The foundations: understanding wormholes in physics. The fabric of space-time. To understand wormholes, we first need to understand the nature of space-time itself. According to Albert Einstein's theory of general relativity, space and time are not separate entities, but are woven together into a four-dimensional fabric known as space-time. Massive objects like stars and planets create curves or warps in this fabric, and this curvature is what we perceive as gravity. Imagine space-time as a stretched rubber sheet. When you place a heavy ball on the sheet, it creates a dip or well. Smaller objects rolling nearby will naturally fall toward the ball because of this curvature. This analogy helps explain how gravity works in Einstein's theory, not as a force pulling objects together, but as a result of curved space-time guiding their paths. The concept of a wormhole. A wormhole is a hypothetical tunnel or shortcut through this fabric of space-time, connecting two distinct points that could be far apart in space or time. The idea is that instead of traveling the long way around through normal space, you could pass through this tunnel and emerge at the other side almost instantly. The wormhole concept arises naturally from the equations of general relativity. In 1935, Albert Einstein and his colleague Nathan Rosen explored such structures in what is now known as the Einstein-Rosen bridge. They described a kind of bridge connecting two black holes, which could theoretically link two separate regions of space-time. Types of wormholes. Wormholes are not all the same. Theoretical physicists have proposed several types based on their properties and the mathematical models that describe them. Schwarzschild wormholes, non-traversable wormholes. The original Einstein-Rosen bridge is an example of what is called a Schwarzschild wormhole. This type of wormhole connects two black holes but is inherently unstable and transient. It collapses too quickly for anything to pass through it, making it non-traversable. In essence, these wormholes exist only as a mathematical solution and would pinch off before any form of matter or information could cross from one side to the other. Thus, while they are fascinating theoretically, they do not offer practical shortcuts. Traversable wormholes. The idea of traversable wormholes was popularized by physicists like Kip Thorne and Michael Morris in the 1980s. These wormholes would remain open long enough for matter, such as a spaceship or even a human, to pass through safely and potentially emerge in another location or time. Traversable wormholes require exotic matter to stabilize them. Exotic matter is a hypothetical substance with negative energy density and negative pressure, which would theoretically counteract the natural tendency of the wormhole to collapse under gravitational forces. While exotic matter has not been observed directly, certain quantum effects, such as the Casimir effect, hint that some forms of negative energy might be possible at the quantum level. Microscopic versus macroscopic wormholes. Wormholes are also categorized by size. Microscopic wormholes would be tiny, at or near the Planck scale, approximately 1035 meters.